All right, so we're going to go ahead and talk about industrial robot history. So chapter one's kind of got three parts. It's got the history. It's got we're going to be talking about what basic robots are and basic robot safety. So let's start about talking about history because history is very interesting when it comes to robotics. Robots in general are based on classified based on their capabilities. This can be under domain of operation, degree of autonomy, goal they're designed to fulfill. So we have what are called ROVs. I don't know if y'all know what those are, but those are underwater vehicles. They're remote operated vehicles, generally used underwater to explore things like the Titanic shipwreck or the Marianas Trench in places that humans really shouldn't be, under pressures that the human body would not last through. So that's one of the goals those are designed to fulfill. There are a lot of different goals like that, just always depending upon what exactly the robot is supposed to do. Sorry about that, guys. I don't know what my computer decided to open that one. I do not know why my computer also decided to open that. Okay, so we have several different types of domains of operation. So what that means is places where the robots operate. Where do they live? Where's their favorite place to be? So we have stationary robots. So these are ones that are fixed in place and don't really move. So these are the robot arms we typically think of when we talk about robots. We have computerized machine tools. So if you ever seen a CNC machine, technically that's a robot. So a lot of industrial robots are stationary. We'll talk about the reason why after a while. Then we have ground robots. These are things like the Mars rover, or a bomb squad robot. I don't know if y'all have ever seen those. If nothing else, I don't know if any of y'all watched any movies or anything like that that have those in them, but they're actually really kind of cool little robots. Since they're made to go and disarm bombs remotely, so you don't have bomb techs getting tangled in those. And so these guys are categorized by their drivetrain. You have underwater as a domain. Again, that goes back to the ROV. You also have autonomous underwater vehicles. These are designed to work at depths that, again, we can't get to, simply because it would kill a normal human. You have aerial. If you've ever seen a drone, that's what an aerial robot is. Essentially, it's just a drone. It's able to fly on its own, or it can be controlled from the ground. And then you have ones that are designed to work in microgravity. So you have the robot arm that's on the space shuttle that they use to launch satellites all the time. If y'all remember those, where they open the big bay doors on the back and they are able to use the robot arm to throw things out. Same thing. Those work in microgravity. Does it make sense to everybody? I'll take silence as a yes.
Yes.
So then we talk about what's called the degree of autonomy. This is the ability for it to self-control. The best way I can say this is how much human interference is necessary. For something like a bomb robot, you cannot teach it every way to disarm a bomb. That's because a bomb can be made a million and one different ways. And and the people that work with them never really know who made it, what they did, how they did it, not anything like that. So somebody has to be able to be in control so that they can observe what kind of incendiary device they're dealing with, so that they can disarm it. Or you have something along the lines of a drone. Most of the time, drones are not flown automatically. There are times where you can set up what's called a flight path and allow it to zigzag over a field or something, or you have a flight path for it to get from one place to another. But at the same time, they are still deeply controlled by a human being. Your car, especially these self-driving cars, those can also be called a type of robot. They move in a three-dimensional plane. So if you have the self-driving robot or self-driving car, and I use the word self-driving very loosely because you are not supposed to take your hands off the wheel or your eyes off the road when you have a self-driving car. There were a lot of lawsuits in the last few years because people thought self-driving meant that I don't have to actually drive, I can let the car drive itself. Nah, that technology has not come forward that far. So the car is not actually autonomous. It requires a human behind the wheel. Now, I will not tell you how many stories I've read about people that decided that instead of staying behind the wheel, they were going to jump into the back seat or the side seat and either take a nap or do whatever else they wanted and let the car drive itself. There's a few people that got arrested over that, as you can imagine. So bad things happened with that. A lot of people got in trouble with that, which is why they no longer classify them as self-driving cars. They call it driver assist. So autonomy is the automatic, is how self-controlled can it be? So an autonomous robot can operate properly without intervention indefinitely and can deal with unexpected problems gracefully. So the Mars rover, the Mars rovers that they have had up there for decades now, had to have a good deal of autonomy. Why? Because those robots had to be able to explore. If it got tumped over, it needed to figure out how to be able to right itself. If it hit a rock, it needed to be able to either go over or around it. Things like that, because a human, the way Mars's orbit and our orbit are, we don't always coincide. We are not always going through this universe at the same speed. So NASA could not keep contact with the Mars rover. It would send information whenever Mars and Earth are lined up enough to send the information, but they could not have constant contact with it. So they created something that would have the ability to think and work through problems like that on its own. So it's able to deal with those unexpected problems through its programming and its ability to say, oh, this is what happened, I need to fix this. It also was able to take samples and stuff as what that it had been programmed to take when necessary. We have what are called teleoperated robots, which a human has to send the robot signals to do its job. Okay. It also can be classified by how self-contained it is. Is everything built into the robot, like again the Mars rover, or is it like an industrial robot where you have the robot itself sitting on the floor and its computer brain sitting elsewhere? All right. Any questions on this, guys? Take that as a no. Industrial robots. So these can be used for a lot of applications. The earliest ones were material handling, spot welding, spray painting. So these were jobs that humans don't really want. So these are jobs that are hot or heavy or hazardous. Forging is one of the big ones. Swing is a big one, and casting is a big one. Welding, I don't know how many people in the class are welders, but welding's a hot, nasty job. And there are some spaces where if a human crawled into it, it would cause severe problems when they're trying to work in it because of the fumes. So that's why you see robots put in a lot of those applications. When it comes to spray painting, there's actually in the old Ford and other car plants, especially out in Detroit, Michigan, where people have gone into the paint booths, the old paint booths, and they have actually, on the rails the cars used to ride on to go from one place to another, have pulled off giant chunks of paint that are about a foot thick, where you had overspray and drip from the cars when people used to paint them. When a robot paints, it does so in very efficient movements. With a human, if you've ever had to spray paint anything, you actually got a can of spray paint and started messing with it, that stuff drips, it drabbles, and it just, you can't get that smooth, even coat. Robots have that great ability to do so. Assembly operations. Humans hate to do same things over and over again for their entire lives. So with assembly operations, if it's very tedious work, a robot is much more capable of doing it without causing mistakes down the line. Palletizing and material handling. If you're having to move heavy stuff onto a pallet, a robot has the ability to do so without hurting itself. There was a company I was working for that did automation. And one of the things that we had to do was there was this company that sold pool heaters. So this is for a giant swimming pools. I'm not talking little ones, big swimming pools. And these water heaters, these pool heaters were huge and they were heavy. So instead of having a human go through and pick these up and put them on pallets and then take the pallets to shipping and we actually created a robot cell that did all that for them. Dispensing operations. So if you've ever had to deal with, let's say, the hospital pharmacy, or there's some of the more higher tech pharmacies, they actually dispense medication where a robot counts the medications. The human does a recount just to make double sure the count is okay. But that's how some places are coming to dispense medication. They do that at UAB and several other places. Laboratory applications. Water jet cutting. If you've ever seen a water jet cut, that thing's really cool. And then we'll talk about work cells later. Educational robots. There are numerous robots for educational purposes. So we actually have some of these on hand. Whenever y'all come to class, not this coming Saturday after this, but the one after that, you'll actually be able to see these run. So how did robots start? And technically, it all started with clock making and automation. So for pretty much ever since humanity came to be, we've always tried to find ways to make things happen without human intervention. There's all sorts of stories about the Greeks or the Romans or the Egyptians who were able for let's just say, purposes to surprise and thrill their population for the deities that they are, the gods they worshipped at the time, would create these marvelous machines or these marvelous wonders to uh, to delight people and to bring revenue to the temples. Um, it's actually really fascinating what they used to do. So one that I can think of was where you would put a coin in a pressure setup, which would then bring holy water out to where somebody could get to it. And there's all sorts of examples of that. One of the other examples is that you have what's called Leonardo da Vinci's lion, and that was in France. He had actually created a mechanical lion that could walk and roar and move its head and move its paws. It was, for the time, if you really think about the time, it was quite amazing. So then you skip a few years forward into 1801, and you have a loom that is more computerized. It's able to go by pattern. So then you have Christopher Spencer, who creates a cam-operated lathe, which is what all modern lathes are based on. You have Stuart Babbitt, who designs the first motorized crane to remove ingots from a furnace. If you don't know what an ingot is, if you've ever seen the movies where they have these giant bank vaults and then you just see this pile of gold bars, that's an ingot. That is the very basics of what an ingot is. The first time the word robot was actually used was in a movie called Rotham's Universal Robot. It appeared, I'm sorry, it was a play, not a movie, but it got turned into a movie. Really interesting one too. But it was called Rossum's Universal Robots, 1923. We have what's called the electronic numerical integrator and computer, which basically was a glorified calculator that used 17,468 vacuum tubes, over 7,000 crystal diodes, relays, resistors, capacitors, and a bunch of hand-soldered everything. It weighed 27 tons and was roughly 8.5 by 3 by 80 feet. Took up 680 square feet of space and consumed 150 kilowatts of power. To put that in perspective, it's about the size of a small home. And all it did was calculate math. Okay? So take a look at your calculator if you've got one, or take a look at your smartphone, and this is where all that started. Okay? 48, you have the published cybernetics, or controlling communication in the animal and the machine. So cybernetics is the study of machines that can analyze their surroundings, adjust their operation to fit said surroundings, and communicate with other systems when necessary. So basically the very basis of all things in our modern world, yeah? So in 52, you have John Parsons, who developed the first numerically controlled machine tool with MIT. Yes, MIT has been around a very long time, and they come up with a lot of really cool stuff. Numerically controlled machines use readable sets of codes to control the activities it's going to do in its operations. So, in other words, if you've seen a water jet cutter, this is the very beginning of that. Okay. 54, you have George Devol, who patented the first programmable robot capable of performing industrial tasks with the formation of his company Unimation. This is where the first industrial robot was created, was in 1954. So they haven't been around that long, but they've been around long enough that that's been around a little while. So this is the Unimate. You have Joseph Engelberger and George Devol who created this. It joined the assembly line at General Motors in 1962 to handle the die-cast machines, which I don't know if you've ever seen a die-cast machine, but it's heavy, hot, and nasty work. But I will say this. So if you notice, there's a gap between 1960 and 1962. So let me kind of explain that in the fact that when they created the robot, they saw something that was a necessity in manufacturing because, you know, manufacturing is great and all, but it comes with its own risks and its own problems. So, and one of the things was that in the 1950s and 60s, you had all these movies come out about how robots were going to take over the world and destroy the humans and everything else. So that was mostly in America that those movies were shown, and it made a lot of people very wary about having those around. It kind of became a bit of a stigma to begin with. However, after they created this, they were able to sell it to the Japanese very easily. And they were able to sell it to a couple other countries, and then it finally took off in America. So the Unimation started working with companies in Japan, starting the worldwide application of robots. The Japanese were very enthusiastic with it. So this is a tabletop robot arm powered by electric motors. So you go from something big and clunky like this, which is the Unimate, to something a little smaller. It's able to be on a tabletop, and it gets a little more motion to it. So in 1971, you have Intel Corp that is able to develop this first microprocessor to control a cash register and store programs to control its operation. So we've gone from all these big clunky vacuum tubes and diodes and everything else, and we're getting to smaller and smaller computer chips. So in other words, we're about to have a computer not take up a whole room. We're about to be able to have a computer become what we think of as an old desktop. Okay. 73, Richard Hahn and a team of engineers from Cincinnati developed the T3 robot, which used a microcomputer, and it became the first one that was able to be controlled by a high-level computer language. So we're just moving right along, right? Moving right on along in the technology world. 76, Viacom demonstrated an electrically operated robot arm controlled by a microprocessor. 77 offered two sizes of electrically driven industrial robots that were microcomputer controlled. So like I said, it's just so we started in what year? We've created the first one in 1954, 1960. So in a decade, we've already got a total change over from what we were doing to what is closer to what we do today. So here we're almost 2 decades out. We've got the Unimation that develops the Puma, or Programmable Universal Machine for Assembly robot system. All right. This one is a robot arm that's arranging chocolate in boxes. And I've got some videos I can show y'all later, that's some really cool ones. This is an industrial robot being able to operate a foundry. I don't know, do y'all know what a foundry is?
No, ma'am, I don't.
Okay. So the very basic definition of foundry, it's that it's a factory that produces metal casting. Okay. So these are cast into shapes by melting them into a liquid and pouring them into a mold. So this is basically things like cast iron. Things like that. So that's what this is. Foundries are the ones that do casting, and if you know U.S. Steel or U.S. Pipe, they're foundries. They do a lot of casting for what they create. These are a pair of 6-axis robots used for welding. So the good thing about robots that weld is the fact that they have a lot more precision, and we'll talk about precision on robots later. But the fact of the matter is also that they are tireless, and then thirdly, they can get into spaces that a normal welder could not get into. This is a hazardous duty robot. These are used by bomb squads across the country to locate and dispose of bombs. Again, you have a camera right here mounted to this robot so that the operator can observe what the robot sees and help the robot to disarm the bomb or to take it off somewhere to where it's not going to harm humans. Does that make sense to everybody?
Yeah, ma'am.
This is a Robug 3 designed to operate in radioactive areas like the core of a nuclear reactor with 8 legs and vacuum gripper feet. It can walk over obstacles, climb walls. It's very strong and it can drag loads of over 220 pounds. Okay. So you would send this into, let's say, a nuclear core that's having a minor meltdown. Things like that. Does anybody know what this is? This is a laparoscopic operating robot. So this is a robot that can actually operate on human beings. This is a robot that can actually operate on human beings and do things like, if you need your gallbladder removed, they can do that. You need if you need heart surgery and things like that, the surgeon has to be able to program it, but the robot is what does the action. Why would we want a robot to do surgery instead of, let's say, a surgeon, a human? Nobody's got a guess. It's the fact that robots have the precision, we do not. There's been more than one person in this world that has been taken out by a surgeon. Okay. So we'll do the next part of chapter 1 in just a second. Does anybody got any questions? All right. All right, so we're going to take a bit of a step back here and we're going to talk about the basics of robots.
George Devall's favorite place, Connecticut, where ideas percolated and inventions were born.
George Devall was a serial inventor. He was a guy who
Sorry about that, guys. I'm trying to...
chose not to go to college because he was so brilliant that he was capable of making a living just by coming up with inventions on his own.
Why does this thing keep pausing itself?
By the mid-1950s, George had helped invent all sorts of devices, such as the doorman that used a photoelectric cell to open doors.
George Devall was kind of a nerdy guy who was really focused on the details. He wasn't thinking about the big picture. He was really focused on how his inventions actually worked. And not so much on whether people would want to use them or what the applications were or anything like that, which is why he wasn't the greatest businessman.
While looking through a technical journal, he saw an assembly line of monotony that set his imagination working. George wondered, why should human beings have to do such mind-numbing work?
You're doing that job again and again and again. And once you do it all day, human beings just lose concentration. And losing concentration meant that you could get injured, and people did.
George thought that if something else were to do all the repetitive work, the workers' lives would be improved. If that tool were to move similar to the human arm, grab onto things and lift them up, its possible uses would be mind-boggling.
It had to be able to pick up heavy parts. It had to be dexterous, so it had to be able to get a hold of those parts and hang on to them and move them to another place and let go of them.
George pictured a machine that had a wrist that could bend and rotate similar to a real hand, with two opposing fingers to do the grasping. The arm's actions would be controlled by a computer, which could be reprogrammed for different jobs. George obtained a patent, but he was unable to find anyone to listen to his idea.
He's really focused on details, he's really technically proficient, but he's not really very good at explaining what he's doing to anyone else.
His break came by chance at a friend's party.
George Duvall, I'd like you to meet Joe Engelberger. I have a feeling you boys have a lot to talk about.
George, nice to meet you. Nice to meet you, Joe. I think we need a drink.
Joe Engelberger was an engineer with a background in physics, who was also a very sharp businessman.
So, George, what line of work are you in?
Well, I had this idea. The two get to talking, and Joe suddenly realizes that what George is describing is something that he's read about in science fiction, only it's real. A robot.
Very interesting.
Joe spotted the huge business potential and all the possible uses for a robotic arm. It was the beginning of a fruitful relationship.
Well, here, Joe. This is it. I know it doesn't look like much, but we can clean all this stuff out of here.
George concentrated on building a working prototype and solving engineering problems that arose. Joe began to identify all the potential uses for a robotic arm.
He was going to factories and he was trying to figure out the lowest hanging fruit. Where can robots help first? So he was trying to identify really important jobs for robots. And that means jobs that people don't want to do.
One of their biggest engineering challenges was how to adjust the robot's grip so it was adaptable for different tasks. The solution was to install pressure sensors inside the machine's hand. The heavier the pressure, the stronger the grip was needed to be. The robot's movements were programmed into a computer.
You just move it through the motions, and then it would record that, and then it would play it back again and again and again, all night long, never going to sleep, never asking for a break.
The prototype was called the Unimate. The duo continued to refine and test it, proving that their invention was adaptable to a multitude of tasks. It seemed as if success was inevitable. But George and Joe had not counted on the image that robots had in the US.
At the time, robots were just like witches or werewolves. They were completely made up. It was just like any other boogeyman that was used to scare people. When robots appeared in popular culture, they were typically killing everybody. So this is a tremendously difficult business problem.
The US's lack of enthusiasm was disappointing. George and Joe had to expand their horizons, and in Japan, the post-war economy was booming.
In Japan, robots were much better perceived, and so there was no drawback for the Japanese companies to tell everybody, hey, we've got robots.
Japanese car manufacturers began to use Unimates, and productivity boomed. The rest of the world took note, and the robot revolution began.
This was a real turning point for humankind, because one minute we were just using tools, and the next minute we were letting tools do their jobs on their own, completely autonomously.
In 2003, the Unimate was inducted into the Robot Hall of Fame. But it was George and Joe who deserved the real credit for working out that almost anything can be made with a robot.
So that just kind of gave you a bit more of a history on it. So, what is a robot? So this is kind of an opinion question. I want to kind of hear what y'all think about it. What would you define a robot as being?
I would define a robot is to be able to do inhuman-like capabilities. Like you said, certain things a human can't do, a robot can pick up in that area.
Okay. Anybody else? So that's not a bad definition. But robots have so many different definitions because I don't know how many of you remember the toy robots that used to come out all the time for Christmas. It used to be the big thing like Roboraptor or the robot T-Rex and things like that. Technically, those can be called robots. They're just not industrial robots. They're toy robots. So there's no precise definition, but the agreement is that it's a programmable machine that imitates the actions or appearance of an intelligent creature. So something along the lines of a dog or a cat or a human. Okay. To qualify as a robot, a machine has to be able to do two things, and that's one, to get information from its surroundings, and two, do something physical, such as move or manipulate objects. That's why I said, technically your car, if you have a really, one of the more modern day cars, technically that can just about be classified as a robot, because what do most cars have? Most cars have at least one sensor somewhere in it to either sense things like the outside temperature or sense the tire pressure in the car, in the wheels of the car, things like that, right? What a lot of modern day cars do is they have a lot of sensors in them to be able to tell you what's going on with the car itself. Okay. So, the way the car does something physical, it moves you throughout the world, right? It has that ability. So we have what's called the International Standards Organization, or ISO. They say that it is an automatically controlled, reprogrammable, multi-purpose manipulator programmable in 3 or more axes. So it's got more than one person. It can have more than one purpose. Reprogrammable is a big thing, and it has to be have 3 or more axes, which we'll talk about what an axis is here in a minute. The next people you need to know are the Robot Industries Association, the RIA. Their definition of an industrial robot is that it is a reprogrammable, multifunction manipulator designed to move material, parts, tools, or specialized devices through variable programmable motions for the performance of a variety of tasks. That is a mouthful. Okay? But that is exactly what most industrial robots are. So what's some of the big things that you've seen so far in these 2 definitions? And the words here that should jump out at you are the words reprogrammable, because that was in both definitions, right? Reprogrammable, so that means that we can do more than one job with it. It's not going to be a single use or single job device, right? And then multifunction or multi-purpose, those are kind of the same taglines you can use on this. So it's not stuck doing one job for the rest of eternity. It's actually able to do more than one thing. Everybody following all right?
Yes, man.
So, like I said, the 2 big things here are that they are reprogrammable. So we can create a program, store it, and use it. But we can also go in and change it, or even go so far if we need to as to get rid of it. Okay. Multifunctional or multi-purpose is that it's capable of performing more than one function or purpose. So it can be, if you've ever seen an industrial robot, it has the ability to not only do something like welding, it can spray paint, or it can assemble, or it can just pick and move. It just doesn't have that one singular purpose. It has multiple purposes, so that you get more bang for your buck that way, if nothing else. Okay. So this must have several of the following. It is not natural, so it's been artificially created. It has the ability to sense its environments. Now, this is a bit of a misnomer. Truthfully, the robot is not a self-aware thing. Okay? Well, what do I mean by that? Well, what I mean by that is that the robot is not, it's not a living thing. So when we say it can sense its environment, it's not a direct sense of its environment. It's a sense of, how to say this? It's not so much a sense of its environment. It has sensors attached to it that are able to run their information through a computer to tell the robot and to tell the robot program that, yes, you can go ahead and do your move. No, you can't. Does that make a little more sense?
Yes, ma'am.
I was trying to find the best way to say that. There really is no easy way to say that. without getting completely and utterly tongue-tied. So it can sense its environment, but I use sense in air quotes just because the fact that the robot is not alive. It does not have, like we have our 5 senses: hearing, taste, touch, smell, right? And sight. So we've got 5 senses. A robot only has the senses we give it, and that again is processed through a sensor. Okay. I said I don't know how else to say it, but a lot of people tend to want to start trying to act like a robot is something that is actually alive. It's not. It has no more thinking ability than a basic boat anchor if you don't have it hooked up to a computer. There is no actual intelligence on a robot. We can make it seem intelligent, but there is no actual physical intelligence. It can manipulate things in its environment. So if you talk about Mars rover, he has different little arms and stuff that he can use to manipulate different parts of and create different scientific experiments. It has some degree of intelligence or ability or to make choices based on the environment or automatic control pre-programmed sequence. Again, this goes back to these things are not, how to say this the best way. These things have no intelligence. The best way I can say this is I'm going to come out and say it has no intelligence. That would be like saying your computer has intelligence. A computer is not a sentient thing. It has the intelligence we give it. A computer can only make so many decisions, but it has to be based on a programmable decision. Does that make sense to everybody? So I guess my thing is, don't tell me that a robot is sentient. It's not. It's a glorified boat anchor unless you have a program or some way to program it. Okay. So the robot is not sentient, but we can make it seem sentient by the things we do. Just to kind of give you a heads up on what all that's about. It's programmable. It can move with one or more axes of rotation or translation. It can make dexterous coordinated movements. And it can appear to have intent. It cannot truly have intent because it is a machine. And that would be like saying your car has intent. I would hope it does not. If your car is that sentient, then you might want to consider other options for a vehicle. Because if that car ever decides it doesn't want to be driven, then you're going to have an issue with it. I'm just saying. So the Robot Industries Association has 4 classes for robots. You have those that are handling devices with manual control. You have automated handling devices with that have cycles. So yeah. Class C, you have programmable servo-controlled robots, which we'll talk about what servo is, with continuous or point-to-point trajectories. We'll get into all 3 of those definitions in a bit. And then you have Class D, which also acquires information from the environment for intelligent motion. Now that intelligent motion might be, oh, somebody's in my work cell, I need to not be anywhere near them. Or it can be more complicated, like, is my workpiece here? Is it in the right place? So that I can come in, do my welding job, and then make sure I don't bump anything on the way out. International Federation of Robotics. So this is the 2014 statistics. So in 2014, a record-breaking number of robots were installed worldwide. In 2018, I'm going to say that this was, so in 2018, it was over 400,000 units per year. Trying to see if there's anything, so if it's over 400,000 that are being installed a year, so you can imagine just how many there are in 2020 these days, or 2021. Okay, so an estimated 1.3 million additional industrial robots installed by 2018. I think we've probably passed that by quite a bit, but you never know. Robots enable manufacturers to reduce direct and overhead costs, making dramatic differences to competitiveness. That's why prices stay so low, guys, because workers require their time to be tied up in everything from taking a break to, think about your work day. Just go ahead and think about your work day as a person. You work a few hours and then you decide, I need a lunch break. Then you might work another couple hours and decide you need a coffee break. How much actual work can you get done in a work day? Always tends to depend on what you've got to do that day, right? Well, a robot does not need to take breaks. That's what's so different about them, is that they don't require, a 15-minute break every 4 hours. But one of the biggest things that people always want to say is that, well, robots steal jobs. If you think about it, the robots are taking the jobs most people don't want. For instance, do you want to be the person that has to screw the cap on toothpaste day in, day out for the rest of your life? What do y'all think? Does that sound like a fun job? Or who wants to have to deal with welding all day, every day, putting yourself in tight positions that could or could not compromise your health? Answer, no one. Another great example I can give you, again, this is from my time working in automation, was we had this one place that dialed us up, and they were looking for a way. This place made gypsum, or in other words, the stuff that creates drywall. If you don't know what drywall is, it's the stuff that makes the walls of your house. So what they have to do to make gypsum is they have to break down limestone by pressure cooking it. So in order to bring the limestone in, they had this overhead crane that would bring it in, put it over the pressure cooker, and drop everything. But then somebody would have to come behind the bucket with a sledgehammer and hit the bucket enough times to make sure that everything had fallen out of the bucket. Now, I want you to stop and really think about what that would mean to somebody having a job. That would mean you have to take this heavy hammer, take it up over your head, and slam it into another piece of metal so that it so that you can knock all the rock out of it. Now, what kind of wear and tear would that put on your body over time? Put quite a bit of wear and tear on your body over time, right? Eventually, your back would start bothering you a lot. And you also have to ask yourself, who would want that job? If they're not paying spectacularly well, if you're only getting paid minimum wage to do this job, that's going to be miserable, right? That's not a job any human being wants. So thus, they wanted to automate it. They wanted to take the human factor out, so that reduces their overhead cost because they're no longer having to pay workman's comp. They're no longer having to continually advertise that position because, eventually somebody's going to get hurt. Oh, so-and-so got hurt, so we move them out of that position. They have to go do something else, or you get fired from it. Why? Because you got injured and you're having to take up workman's comp again. So that's the kind of job humans don't want that a robot is perfect to take. So the way we automated it was we had the crane that was automated, and then we had a pneumatic hammer that would come out and hit it instead of having to pick up that sledgehammer. So, like I said, don't ever let anybody get away with saying robots take jobs. The fact of the matter is they take the jobs humans really don't want or that humans really can't do. Okay? So assembly robots, they're great for doing the repetitive, monotonous tasks that we as humans don't really want. Everything from screwing the cap on toothpaste or putting caps on products to go on shelves to boxing things up, palletizing them, stuff that would be repetitive motion tasks that they were saying earlier in the video, that's something that humans start making mistakes on because it gets repetitive, it gets boring, and eventually you lose what? If you're doing a repetitive and boring task, eventually you do what? What happens?
Boards start breaking down a little bit.
Your concentration starts to break. And if it's a dangerous task you're doing, or an especially monotonous one, that could cause a lot of problems. Again, you end up with a lot of defects that way. So if you give that task to a robot, you've created created a higher level job, but B, you have taken out a job that might have caused somebody to cause harm to themselves or those around them. So mass production, this is very common. That's where you create large quantities of a single product. So you set everything up and you just let it go for however long you need to create the number of products so you don't have to go back and do it again. I will say there is one problem with that, and that's the fact that and batch work tend to end up giving you a surplus of stuff. And if your product doesn't sell necessarily quick enough to get rid of the surplus, you end up holding on to it for a while and you can't actually end up getting stuck with it. That's not exactly a good thing. Okay. Batch production, you do small quantities of different items, but you still are going ahead and making them there. Then you have hard automation. These are machines designed and built to run a single product. These are not reprogrammable. These are not reprogrammable, so these only have one job and one job only. They can't take up another job. So as for categories, we have project, we have job shop, batch, and repetitive or continuous. And before we get into, so let's go on to the manufacturing categories. We have project manufacturing. So these are one-offs. These are non-repetitive activities. These are generally one-of-a-kind things. They're made-to-order products, so things like bridges, any kind of construction, things like that. If you want to go back to something like project manufacturing, let's see. So basically, this is unique builds. Things that will never be done again by anybody else, or it won't be done very often by anybody else. Does that make sense? So it's a one and done. It's supposed to be unique, completely and utterly unique to people that do them. So road projects are unique. Why are road projects unique, by the way? What do y'all think? Maybe a better question is, are any two roads really alike? What do y'all think? Are any two roads across this whole US exactly alike? Y'all hear me?
Yes, ma'am. Sorry, I was fixing something. But it looks like it's only me and like one other person still in class.
Well, there's technically three of you because somebody's in the other room, is in the course room. So this is a secondary room I've got set up so that this helps me take attendance more easily.
Mm-hmm.
So he's set up in the other room right now because he couldn't get into the first one. Into the room.
All right.
So road construction is going to be unique. Why?
Because no road is going to be identical to the same one because it's a different engineer designing it.
Well, there's that, definitely. But there's also the fact that terrain's going to be different. Heat, humidity, and everything else you've got to go through to get any kind of a road built. And then for bridges, you're right, that's going to be very unique because that is completely dependent upon the engineer who decides to design it, as well as how they design it and exactly what they are looking at when they design it, if that makes any sense. For instance, you can have two bridges across the same strip of water, but one might be a footbridge, one might be one for cars to drive over. It just always depends on the project, right? Same with any building. No two buildings are exactly the same because, everybody wants to do some sort of customization to said building. So job shop, you almost never get the same thing twice with a job shop. Even when you do manufacturing, mass manufacturing of homes, so by those I'm talking about trailer homes that are pre-manufactured or pre-made before they're brought to site. Y'all know what I'm talking about? So the ones I'm talking about are the ones that you'll see getting, getting hauled down the road. Now, they're very similar in construction in the fact that the outsides are just about always the same. They're vinyl siding with a roof and everything else, but the layout inside is what can generally be very different. because the house becomes assembled on site, we generally don't get to see exactly how different they are on the inside of these houses. But no two are exactly and completely alike, because everybody's going to customize it to some degree to their own taste, right? All right.
When a highly specialized product is needed in very low volumes, usually on a customer order basis, the process generally used is called a job shop.
A good example of this is a tool and die shop. In the tool and die shop, precision metalworkers manufacture durable, customized tools that are used to stamp out parts, forge steel, or act as a mold for liquefied metal or plastic. The equipment can produce a wide variety of parts in very low volumes. In this example, a special stamping tool is required to produce engine gaskets. The tool designer receives the specifications from the customer and designs the part on computer-aided design, or CAD equipment. The CAD equipment allows the operator to quickly design an almost endless variety of products in a very short period of time. From here, the machine shop begins to grind the metal into the required dimensions. Holes are drilled and tapped, and the pieces are locked in place. This one-of-a-kind tool is now ready to be tested, and sample parts are stamped out using the new tool. Precise testing and measuring equipment ensures specifications have been met. In each step of this process, the equipment used could also be used on a wide variety of other machine tools. Because every project is custom-made, the equipment must be flexible enough to change with each new job. But since producing a large volume of product isn't necessary, the process can be geared toward providing an exact custom product.
So it's all about the flexibility with projects, right? This one's showing a robot that tends 3 different machines. Excuse me. So you can actually literally follow the arrow here. So he starts off here at the conveyor belt and brings it over to this machine. This machine's going to do its job, then the robot's going to bring it over to the next machine, which looks like a drill press. So the drill press will do its job, and then the robot will pick up the part again and take it down here to the last conveyor belt to go off and do what it needs to do. So what would be a good thing about a job shop or a project shop, project level? Is that you get a lot of customization, right? But the downside is that if people can't afford customization, you end up with what? You end up making money, right? That makes sense to everybody? So then machine tending. So this is all about machine tending. We've kind of talked about it a little bit, but this is just kind of gives you an actual physical example of it.
Fennec Robotics Authorized Integrator Trantec Automation Corporation designed this new automation concept for a series of camshaft machining centers that traditionally use separate linear motion
and floor conveyors. This new 7th-axis robotic design, which utilizes Fennec R2000 IB rail-mounted robots for the amount of fixed automation equipment required, cuts 4 individual automation systems down to 1, uses less energy, and frees up floor space while providing capital equipment flexibility. By integrating
these top-loader Fennec R2000 IB material handling flying robots on an overhead rail, separate fixed automation can be removed at each of the CNC machining centers.
Each machining center had a linear gantry delivered camshafts to and from a conveyor on the shop floor. In this new design, overhead robots pick up and deliver parts from cell to cell. Each movement to the machining center includes removal of a finished part and delivery of a raw part. The traditional design also required hundreds of feet of fixed floor conveyors to feed the machining cells. The new configuration by Trantech eliminates the entire conveyor system, freeing up valuable floor space. Removed, operators and quality control personnel can move freely around the machine centers. But one of the biggest benefits is capital equipment flexibility. The CNC machining cells can be upgraded or replaced without changing the automation system. Because the FANUC robots can be programmed for variable part positioning, exact machine location and alignment is no longer critical. The manufacturer also has the flexibility to reuse the automation and install a completely different line in the future. The FANUC robot programming by Trantech engineers also includes the ability to park one robot and use a single robot to feed all machining centers. This feature virtually ensures there will be no downtime in the system. By integrating standard automation products and by simulating reach studies and cycle times in advance, a faster design build cycle was accomplished. To learn more about Trantech's full line of robotically
So machine tending or flexible manufacturing means that we can move things around where we need them, how we need them. So fixed manufacturing tends to be very rigid. It does not change easily, right? And then if something goes down and our cycle times increase, that means that less work is being done. That's not something you generally want in manufacturing. So flexible manufacturing allows for one cell to go down if necessary, and the other cells can pick up the slack without total cause and damage. Just kind of keep that in mind, guys.
The Flexible Manufacturing Cell, FMC. This is the individual automated manufacturing unit in your company. The size is determined only by your requirements on productivity and throughput times. Here, for example, you can see me in operation in a large milling cell, in which up to 4 different milling processes can be carried out simultaneously. Up to 4 different milling processes can be carried out simultaneously. I adapt myself all the time to every situation. Good reason. I adapt myself all the time to every situation. And how does this benefit our customers? Superb cost effectiveness. And how does this benefit our customers? Superb cost effectiveness. Automated handling with me, the chameleon, is efficient in every extension stage of your manufacturing cell and always a sound investment because I have a consistent
Alright, so I'm just going to kind of talk over this. The whole thing about flexible manufacturing is that you don't want it to do just one job, you want it to do multiple jobs because that way you don't ever really get downtime on that machine. You have it continually in motion, which means that it's earning its keep, right? That's what we want from most machines, right? We don't want it to go down. We want it to continue to run. Kind of like your car, right? You want your car to run all the time. You don't want it to go down because if it goes down, then that means you can't go anywhere. You don't get anything done. Same thing with having flexible lines like these is to go ahead and have it be able to do multiple jobs at once. This is going to show us an automated assembly. And again, this is just some different types of manufacturing so that you can kind of get an idea of why. So this is a little bit more of a rigid manufacturing because changing out a lot of this would be really hard, right? So for something like this, it has to be for something that won't change over time, or if you need to make changes, they'll have to be very minor. Okay. And then this is some metal stamping, but like I said, I'm trying to get through some of these, guys. So continuous manufacturing. This is where you do a very large volume with low variety. You get specialized equipment for very narrow range of function. This doesn't use robots very much. Why? Because why would you need it? If you can get machines that will basically do the job without having to have something that needs to be reprogrammed or moved or changed, then why not build it in and make it permanent? There might be some small things you can go in and change, but for the most part, it's kind of like if you're a manufacturer of toothbrushes. Well, there's only so many configurations you can make of a toothbrush, right? At the end of the day, you don't need a robot to sit there and make the toothbrush. You can just have a specialized machine that goes and makes the toothbrush and sends it on down the line. Okay. So for something like this is a car manufacturer. I'm not sure which one it is because lines tend to start looking a little bit the same. So as you can see, you've got the welding robots coming in and pushing the welds in together. All they're doing is some spot welding. Fusing things together. So do you need to have flexible manufacturing for something like for this kind of a job? What do y'all think? Does it need to be flexible? The answer to that should be yes, it needs to be very flexible, because think about it. Year by year, or even every couple of years, if not every year, they change up how they manufacture things, right? Because they've changed up at least one small part of the car so that it looks semi-unique each time. You might have to produce, the run of one type for maybe 2 years, and then you go up and change the design just a little bit so that you can sit there and say, it's the all-new Toyota Corolla. Okay, so what's new about it? We just shortened the body a bit. Okay, so it's not really new, is it? Same engine, same everything else. But the way they have to change up the robots is they have to go in and change the programming so that the welder is set up to weld in the correct sequence and in the correct places so that it creates that nice strong car body. So these guys have to be flexible. So with robots, most accidents occur during programming and testing and inspection and repair. Okay? So we have robot safety as one of the highest things you have to think about. I'll put it to you this way. Don't ever expect a robot to think about your safety. That has to be whose job? Whose job is it to make sure that you go home every day?
Yourself. It's your job.
It's your own job, right? It's your job to make sure you're acting in a safe manner so that you can go home that day in one piece, right? So that's why I'll say this. It's very much should be on the top of your mind, the biggest thing in your head when you're dealing with anything mechanical, and that is safety first, foremost, and always. Because when you stop thinking safety is when you're going to get hurt. Don't ever expect somebody else to sit there and go, oh, you're not behaving in a safe manner. That should be up to you. So safeguarding is determined by, safeguarding and training are determined by the ANSI, which is the American National Standards Institute, and the I can't remember what RISA stands for right now. And OSHA is also involved because anytime safety's involved, OSHA's involved, right? OSHA sits there and goes, yes, we want to be involved. We want to make sure you're acting in safe manners. And you're not trying to make everybody do something that's not safe. Right? That's OSHA. All right. But companies typically will implement their own safety standards just to make sure that they are covering all their bases. Makes sense though, right? Cover all your bases. So work cell design, it has to take into account the task the robot is to perform. It needs to take in where the robot's going to be located, what kind of startup and programming procedures need to be done, what is going to be the normal run or mode of operation, what kind of malfunctions and corrective actions might need to be taken. So let's say it starts going haywire. What kind of corrective actions is somebody going to have to get in that work cell? Is the work cell big enough for somebody to get in there with it? So electrical, hydraulic, pneumatic, mechanical, store energy hazards. So if there's capacitors or inductors in there with the robot, hydraulic and pneumatic pressure can cause some problems. I don't know if any of you have ever worked on your car or had to change the oil in your truck or whatever you drive. But anything stored under pressure tends to have its own hazards, yeah? Namely the fact that if you're really not careful with some of it, it can inject that stuff under your skin and make you really ill. So that's something to always be aware of, is what kind of stored power it might have and how do I need to vent out that power so that I don't end up hurt. So if it's hydraulic powered, maybe I have a hose crimped somewhere. So I need to make sure that everything that's part of that system is drained back to the tank before I begin working. And I need to make sure everything is shut off to where I'm working at so that nothing gets switched on either by accident or, God forbid, on purpose. Simply because you don't want to get pinched by anything hydraulic. Hydraulics are quite strong. Okay. Then you also have mechanical, store energy hazards, so something that might have a spring or something like that. And you need to make sure everybody's aware of shutdown and lockout tagout procedures. Now, lockout tagout, are those the same thing or are those totally different? What do y'all think? The answer is no, they are not the same thing. Lockout means you have a physical lock, like a gym lock or something like that, a keyed lock of some sort that makes sure that the machine cannot be turned on while you are in the cell or when you're in the area approximate to it and doing any work on it. Tagout can be used with lockout, but it is not lockout. Tagout is something you only should do by itself if and when the machine itself cannot be locked out. You tag it out and let everybody know that that is why that is tagged out. I will go ahead and say this, guys. I'm a safety nut, so there's a reason I'm emphasizing some of this. It should always be top of your mind to be careful about stuff like this, and lockout tagout is how a lot of people get hurt. because they don't do it, and they, somewhere, some way, somehow, things get turned back on and somebody gets hurt. So make sure you are aware of how to do lockout, tagout, and what procedures you need to follow according to the company you work with. For safeguards, we have fixed barriers, interlock barriers, we have presence sensing devices, e-stop buttons, braking, awareness devices, and warning systems. Not all of this will be part of your setup. Sometimes it's only one or two things that'll be part of it. Okay? You might just have fixed barriers to make sure everybody keeps out. You might have pressure sensing devices if the robot's out on the floor. Excuse me. If the robot is on the floor by itself, it might just have pressure sensing devices around it. In which case you really need to be careful, because you can very easily set those off and it may or may not make the robot turn on, and you could end up being sent flying, or it'll make the robot stop right in the middle of what it's doing. We won't even talk about how dangerous that could be to both the material it's working on, its area in the work cell, and everything like that. The most common thing you'll see is some sort of gated barrier around a robot. This is the most common way to keep people out. However, if people have to be in with that robot, there's several different ways that we do that. One is pressure mats, so that the robot cannot be activated while you stand there. Second, you have light curtains, or you have some sort of light beams that are crossing back and forth, so that if you break that beam, it knows you're there and it can't go forward. Okay. You have latch out controls. Yeah. Any questions on any of those? Like I said, the most common you're going to see is an actual physical metal cage around the robot. And that just keeps any and all intruders from coming in and getting themselves in trouble. Okay. These are the control devices, or what are known as teach pendants. These are actually what tell the robot, this is your job, I want you to do, so go do it. It's how you program the robot, take it through its steps and everything else. Does that make sense? I'm going to assume so. Installations can be where you have some trouble too, simply because most of the time these robots are several hundred pounds. You're bringing overhead that may or may not have the ability to fall and crush you. So always really pay attention to what's going on around you. That is typically the best advice I can give you. Be very aware of what's going on around you, who and what is around you, as well as making sure you're where you need to be, so that you are out of the way, but you are able to be doing what you need to do. And since it is 12:10, I'm going to leave it there for the day. We have one more part to cover for Chapter 1, and we will do that next Saturday, as well as going into Chapter 2.